So we were saying that carbohydrates are, again, polyhydroxyaldehydes and polyhydroxyketones. We know something about how hydroxy groups, namely alcohols, behave, and we just learned something about how aldehydes and ketones behave. Carbohydrates are so called because of their molecular formulas. It's as if they were made up of an equal or roughly equal number of carbon atoms and water molecules. Now, of course, that's not literally what carbohydrates are, carbons with waters stuck on them. That's not literally what they are. But if you looked at the molecular formula, let's say, of glucose, it's C6H12O6. And I think you can see, well, we have 6 carbon atoms, and over here, H12O6 looks like 6 H2Os, right? And we'll get to the structure of glucose today, I have no doubt. And you'll see it's not literally 6 carbons and 6 waters, but that's a general rule for carbohydrates. The number of carbon atoms and the number of waters in the rest of the formula will be either equal or pretty darn close. Another example is sucrose, table sugar. It's C12H22O11. I don't care if you memorize these formulas. But that does happen to be the formula of table sugar. Or if you go to the restaurant and you get the packets of white sugar, that would be it. It's a C12H22O11. It's actually a disaccharide containing both glucose and fructose. So in any case, well, we've clearly got 12 carbons. How many waters? Well, not 12, but 11. There's 11 waters in C12H22O11. But I think you'll agree 11's pretty close to 12. And I think if you were to look at the, again, not structure, but molecular formula of any given carbohydrate, take your pick, you'll find that to be true about its formula. It's either the same number of waters as carbons or pretty darn close. So that's pretty much why we call them, just double checking. According to this, we're recording now, so we should be in good shape. Right. So that's in general true about the formulas of carbohydrates. And just to get some terms down, you can further break carbohydrates. One way of breaking them into 2 groups is into aldoses and ketoses, which you can tell by the prefix, as the name implies. An aldose is going to be a sugar that's an aldehyde, that has an aldehyde group. And a ketose is going to be one that has a ketone functional group. And both exist. And I'll just say up front, by the way, I'm certainly not going to be expecting you guys to memorize whole scads of structures. There might be 1 or 2 that I think are pretty important and might do you some good later down the road to, can you change the camera view? Maybe. I can do the webcam. Would that actually show me up like, yeah, there we go. You can always do that. Is that actually better? Do you really want to see me up close like that? That doesn't really help you to see the screen, but you can see the screen anyway. Maybe we should do that. We should have been doing that the whole time. You get to see me with my motorcycle helmet here. Okay, well, if you guys like that better, we'll do it all the time. Good. So where was I? Aldoses and ketoses, right? So and you can tell just by looking at the structure whether there's an aldehyde group or a ketone group, and you should have one of those 2. Sugars should have, natural occurring sugars should have an aldehyde or ketone functional group. And all this is in the class notes, by the way. I just thought I'd make mention of it so you knew what you were looking at when you got there. So you can also name sugars, or I should say classify sugars by how many carbons they contain. And all of these names will end in ose. So when you hear something called a triose, like glyceraldehyde, which we'll meet in a moment, is a triose. 3 carbons means it's a 3-carbon sugar. 4 carbons would be a tetrose. 5 carbons would be a pentose. Ribose and deoxyribose that we met in chapter 18, those are pentoses. And then you have hexoses. Glucoses is a hexose. What else is a hexose? Not lactose. Galactose is a hexose. And glucose and galactose together in a certain way makes lactose, which is milk sugar. And so some people are lactose intolerant, and you need to take a pill in order to, which is actually nothing other than the enzyme that you're lacking enough of, in order to have your milk or your ice cream or what have you. There's a pill, yes. Well, there's certainly a pill for lactose intolerance, but not, again, I'm not a medical doctor, but my understanding is not all lactose intolerance is the same thing. There is a kind that, yeah, you can just take lactase enzyme. It should be available over the counter. But there's other things that can go wrong in how we digest milk and dairy products that maybe that pill won't be enough for. Well, and again, this is my best understanding, but I'm not a medical doctor. I have heard one interesting thing though, which again may or may not be true, but so definitely look into it if you're curious. But what I've heard is that the United States is one of the few countries where most of us are not lactose intolerant. So, but you know, double check me on that. That was my understanding, but I could be wrong. Good. So you learn more here by accident than elsewhere by design some days. Good. So fact checker going. Okay, well, that's fine. You know, if I'm wrong, I'd like to know. In the end, there's probably about 2 structures that I think are going to be good for you to learn. One of them is the structure of glyceraldehyde, or at least of D Galactose. And there's 2 ways of drawing that. One way using wedges and dots that we're kind of familiar with would look something a little like this. Trying to paint that wedge. And so we'll have a hydrogen over here, OH over here, and then dotted bonds. We'll have our aldehyde group up here. So this will be an aldose, certainly. Remember, CHO is an abbreviation for aldehyde. You don't have to use the abbreviations if you don't like them, remember. If you would rather write C double bond O and then put the H in the carbon, that's fine. You do not have to use these abbreviations. All I ask is that when you see them, you understand them. That's the main thing. And one question I always get is, how come we write CHO instead of COH? It's a fair question, but COH makes it look like it's an alcohol. And so, you know, long decades ago, maybe even over 100 years ago, they decided to write CHO instead of COH. And then on the 4th and final bond, CH2OH. And that's very typical for an aldose. You'll find at one end of the molecule, you have your aldehyde functional group. The other end will typically be CH2OH. And then there will be one or more chiral carbons that look like this. Of course, the top and bottom carbons here are not chiral. This carbon is sp2 hybridized, so it's not chiral. This is a CH2, so game over, not chiral. But this carbon is chiral. And so you'll find one or more of this type of carbon differing only in which side the OH is on and which side the hydrogen is on in any carbohydrate. And then there are ketoses also. If you're interested in ketoses, you can look up the structure of fructose. That one is a ketose. And you'll see it's not too different, except we've got CH2OHs both at the top and the bottom, so to speak. And instead of the top carbon having your carbonyl, it'll be the next one. So after the top CH2OH, if that's carbon 1, then you'll find carbon 2 will be ketone for fructose. What is its function and where can we find it? Well, first of all, let me write out, it's D Galactose. And it does show up in living systems. It's a naturally occurring species. My understanding is it's mainly used or it's mainly found in some of the biochemical pathways. I think you will find glucose breaking down to a couple of glyceraldehyde molecules in glycolysis, for instance. But in terms of its biological function beyond that, what it signals for, that I'm afraid I can't tell you. I just am not familiar enough with molecular biology, but that's not really a part of this class anyway. But that's D Galactose. And if you know that structure, then you automatically know the structure of L-Glyceraldehyde, which is simply the enantiomer. So that will have the OH on this side. By the way, notice that I'm being very careful to write HO on this side. I'm doing my best to make it clear that it's the oxygen that this carbon is attached to. So whereas we can afford to be more flexible with abbreviating carbon groups like methyl, it doesn't generally matter a whole lot whether you write H3C or CH3. With oxygen, we can't afford to be so sloppy because it is only 2 bonds. So we can always be careful to show the connectivity unambiguously. And this guy would be L-glyceraldehyde. And I think you can see what's making the difference. It's that chiral carbon. And specifically, the D sugars, first of all, I'm having trouble writing aldehyde, just a moment. Normally I can multitask, but I was having trouble with aldehyde. What's going to turn out to make the difference as to whether a carbon is a D sugar or an L sugar is you're going to want to look at there's a $60 word for it, the penultimate carbon, which means the next to last one, the next to the bottom one. So this is the last one, that CH2OH is the last carbon, and this carbon here is next to last. That's what they mean by the penultimate, next to last. Or penultimate carbon if you want to use fancy words. And you want to look at the OH group on that next to last carbon. As it is, it's the only chiral carbon in glyceraldehyde, but the pattern will work for other larger sugars. And for the D sugar, the OH group is on the right side, and for the L sugar, it's on the left side. That's the difference between D and L sugars. And I should quickly add that otherwise, the difference between the two is it's the D sugars that are natural. These are the ones that occur in living systems. Whereas the L sugars are the unnatural ones. These ones do not occur spontaneously in living systems. They exist. L-glyceraldehyde is a thing. You just won't find it occurring naturally. It needs to be made in the lab. So you can take a guess as to which one of these is cheaper, probably by multiple orders of magnitude. But I think that's important because they're going to assume all that, I think, in your biology classes, that you've heard of D and L sugars and know that the D sugars are the natural ones. Just a word of warning coming down the pike, unfortunately, and for reasons I don't really understand, but unfortunately, the opposite is true for amino acids. I don't know why. But whereas it's D sugars that are natural and L sugars that are unnatural, it's L amino acids that are natural and D amino acids that are unnatural. If I had to take a guess, if you absolutely put me against the wall and made me guess, my guess would be that if you looked at the pathway that interconverts sugars and amino acids, which certainly does exist, I wouldn't be surprised if there were some reaction in there that were, hey, like an SN2 reaction, and inverted the stereochemistry at that carbon. That would not surprise me in the slightest. I don't know that for a fact, though. That just would be my guess. But it's just one of those things like that word benzylic that we're stuck with. You know, it's D sugars that are natural, but L amino acids that are natural. Good, so I think that's all I really need to say about that. And I think D-glyceraldehyde is an important enough molecule and a fairly small one that it's worth you guys knowing that structure. Of course, if you know that, then you have L-glyceraldehyde thrown in for free. It's just the enantiomer. Let me show you also something else. You will commonly, when it comes to carbohydrates, run into these so-called Fischer projections. And that's a way of abbreviating the whole thing even further. And so the equivalent Fischer projection for D-glyceraldehyde would look like this. And all you do is you make a little diagram with crossing lines like this. So that's what we call a Fischer projection. Pretty sure it's SCHER. I'll just go PROJ period for projection. And the only changes you make are you don't use wedges or dots. Those are understood. It's understood in a Fischer projection that the horizontal bonds are wedge bonds and the vertical bonds are dot bonds. So it's a way of shortening it further. The other thing, and this is very important, you must not put a letter C at these intersections here. As soon as you do that, it's no longer a Fischer projection. It's a valid structure, but it's not a Fischer projection any longer. There's no stereochemistry implied. So do you see how I just leave this as an intersection of those two lines? So those will be carbon atoms as they normally would be for us anyway, right? Like in any line angle drawing. But those are really the only two differences. And I'm only mentioning that because you will see these things particularly with carbohydrates. And I think there's a very good reason for that. Probably by the end of the lecture today, we'll get as far as D Glucose, which now is 6 carbons. And boy, it's so much more convenient just to be able to go, and draw 6 carbons quickly like that, than to have to go wedge dot, wedge dot, wedge dot each time. This is not wrong though, and there's nothing wrong with that structure. I just think you'll agree with me that this is quite a bit more convenient. Maybe one last thing that occurs to me about Fischer projections. Well, actually, before I say that, we can always look at the Fischer projection for L-Glyceraldehyde. Again, that penultimate OH determines whether the sugar is D or L. I think you will, in general, find there will be a penultimate OH. I guess if you're looking at a deoxy sugar where both of these are hydrogens, well, then I guess it's neither D nor L. I've never heard of a compound like that. I don't think they exist. But in general, I think you'll find there will be a penultimate OH, a next to last OH group. So that would be what the Fischer projection for L-glyceraldehyde would look like. But one other thing about whichever Fischer projection you want to look like, something that biologists and biochemists do a lot is they will just leave the H's off and just leave this stick like that. I am not a fan. I don't recommend doing that. Let's at least not do that in this class. I'm not a fan of that. I think that can be confusing because it makes it look like there's a methyl group there if there's just a stick sticking out. But just to give you guys fair warning, when you get to your upper level biology and biochem classes, you will see that kind of thing a lot. I'm not going to do that here, and I'm going to recommend that you guys also not do that. I think it's too potentially confusing. I'm sorry to just say D and L. Yes, that's exactly right. It's the D sugars that are natural and the L amino acids that are natural. I don't know why, but that's exactly right. What you said in chat is exactly right. Don't really know why that is. CHO at the top. Where did I put C? Ooh, crap. Sorry about that. Thank you. Yes, that's wrong. That compound's a thing, but it's not L-glyceraldehyde. There you go. That's L-glyceraldehyde. Thank you. Please make that correction if you got that down in your notes wrong. Yes. Actually, I think we'll eventually learn how to make that. Maybe Friday, maybe Monday, one of those two. There are some typical reactions of sugars. Good. So much for smaller sugars. Let me show you also where D and L comes in. Let's say that we drew a bigger sugar. Let's do something like this. Oh, actually, let me also draw a ketose. Why not? What could possibly go wrong? I don't think I've killed anyone yet from drawing a ketose. So a typical ketose will have CH2OH in the top carbon. And then your ketone comes next. And let's make this one have 5 carbons as well. 1, 2, 3, 4, 5. There you go. So there's a typical ketose. Both of these also will be pentoses because they have 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Of course, it's fine to put a letter C here because that carbon's not chiral, right? It's sp3 hybridized. So no need to worry about that. Which then begs the question, what are those compounds? And the answer is, I have no idea. But I do know that this one is a D sugar because the next to last OH, the penultimate OH, is on the right. And I know that this one is an L sugar because the penultimate OH is on the left. What they're called, I don't know, and I don't really care, and I wouldn't expect you to know either. But I certainly would expect you to be able to identify correctly whether a sugar is D or L. And you always do it regardless of whatever else is going on in the molecule. You just hone right in on that next to last, that penultimate OH, and that will tell you whether you're looking at a D sugar or an L sugar. And in all cases, the enantiomer of a D sugar will be an L sugar, the enantiomer of an L sugar will be a D sugar. No exceptions. That will always be true, whether it's 3 carbons or 6 carbons or 60 carbons. That would be scary looking. Imagine a 60 carbon long Fischer projection. Now I'm going to have nightmares. Okay, which means I can only imagine what you guys are thinking about that. But be that as it may, so much for smaller sugars. And like I said, I can't think of really any tetroses or pentoses that you're going to need to have memorized. I mean, maybe ribose would have come in handy back in chapter 18, but I don't think even there you had to memorize. I don't think I made you memorize that there either. But in terms of sugars that are relevant to us, I think it's best to skip straight to 6 carbons because that's when things get interesting. Let me see now, we're at 3:30, I have another 15 minutes. I just want to, let's see, we did D and L sugars. I just want to make sure I'm not missing anything. Yeah, we're ready for glucose. Good. Oh, and I should mention, by the way, certainly 7 carbon and 8 carbon and so forth sugars exist. We're not going to run into any, certainly. And I would be shocked if you ran into too many of them in even your upper level classes. Good, so let's erase this and let's consider glucose. Glucose is an important enough molecule that if you had to memorize one of the D-hexoses or D-aldohexoses, let's say, those 6 carbon sugars that are D forms, so they occur naturally, and are aldehydes also. If you had to memorize one of them, and as I hope to demonstrate in a moment, there's 8 of them total, but if you had to memorize one of them, I think glucose, D-glucose would be the most important one. Let me see. So the way I always remember it is right, left, right, right, as to where the OHs go. Right, left, right, right. So again, that all-important penultimate OH here is on the right. That means you're looking at a D sugar, so this is D-glucose. This is the most common sugar that you'll find in the bloodstream, and it occurs also in a lot of fruits, you know. I think grapes have a ton of glucose in them. So that's how I remember. I just remember right, left, right, right for the 4 OH groups. Now, if you think about it just for a moment, where did I get that there were 8 possibilities for this compound and its brothers and sisters, so to speak? All of the ones that have 6 carbons, all of the ones that have an aldehyde group, and all of the ones that are in the D configuration. Well, if you think about this just for a second, so the CH2OH has to stay the same. Certainly the aldehyde group has to stay the same. and the configuration of this carbon has to stay the same. Because if you flip that, you don't have a D sugar anymore. You've got an L sugar. These other three, the ones that are right, left, right, those three can vary, and we will have a compound similar to D-glucose. It'll be a diastereomer. Oh, there we go. But it will be a diastereomer of D-glucose that still is a D sugar and still has 6 carbons and still is an aldehyde functional group. So if you consider that any of those three can vary, well, each of those OHs can be either the left or the right. So if you work that out, it's 2 times 2 times 2. There's 8 possibilities, of which D-glucose is one of them. And you'll have heard of some of them. D Galactose I mentioned. There are some other funny names. You got like Altrose and Allose and Mannose. They all have names. I certainly don't expect you to memorize all of those other 7 compounds. If you take some biochem later on, you might well have that pleasure. I will certainly not ask you to do that. Why? Because for my money, if you know glucose, then you automatically know those other 7 compounds by comparison. For instance, not to sound like that guy on The Matrix, but what if I told you that D galactose is just like D glucose, except at carbon 4? Carbon 4 is the one where it differs in configuration. Well, we can number the carbons. That aldehyde carbon, which we by convention put at the top, will always be carbon 1. And we will find that there are 6 carbons, just as we thought there would be. So what would the structure of D galactose be? Well, this is why I really don't care if you memorize D galactose. Because in order for you to be able to draw it, all I need to tell you is it's just like D glucose, except it differs in configuration at carbon 4. So we'll keep everything else the same. We'll just flip carbon 4, and we will have ourselves D galactose. So this is carbon 2. We'll keep that the same. Carbon 3 is also the same. But carbon 4 will flip. Instead of the OH being on the right, it'll be on the left. And again, notice that doesn't make this an L sugar. It's still a D sugar because the configuration of the penultimate OH is the same. That's still on the right. And so that would have to be D galactose. Good. So if you can draw some of these things in this so-called straight chain form, I'll be happy. I want to go over the cyclic forms, and we still have 10 minutes, so I'll probably be able to get into that at least somewhat today. I don't think we need to go that far with all the Hayworth projections and chair projections, and it would get a bit hairy. But I think at least being able to draw a couple of these things in the straight chain form, that's straightforward enough, and I think that might be helpful to you down the road. Here's another one. What if I finally learned how to do this? Let's see. This could be very impressive. Oh, ooh, you know, can I even copy it with control? No. Oh, well, that was cool while it lasted. In that case, what I'll do is I'll move my galactose over, and let's ask a different question. Let's ask ourselves what L-glucose would look like. Which would be the inverted glucose, glucose not of the sort that you would find in the bloodstream or in any fruit out there. It does exist and you can buy it. I bet it's stupidly expensive, but you can buy it. Or maybe you can't, maybe even I can't, but you know, researchers or people in industry can buy it. Well, what we would do is we would flip all 4 of the chiral carbons. L-glucose is nothing other than the enantiomer of D-glucose. So instead of right, left, right, right, it'll be left, right, wait, yeah, it'll be left, right, left, left. Right, so we'll flip where that OH is. We'll flip this one also so that it goes to the right. The OH in carbon 4 will be to the left. and the OH and carbon 5 will also be on the left, which is what determines it. That makes it an L sugar. So this just gives you some idea of the different stereochemical possibilities. None of this is terribly different from what we talked about back in chapter 5. It's just the molecules maybe are a little bit more complicated with several chiral carbons in them. But the ideas are no different. If you understand the material in chapter 5, then you can understand these types of things. Good. So I think that's all we need to say about that. What I would like also to go over then, actually, I need for that reason to, let me just go back to the screen. I really would like to open up your class notes because I put all the structures in there for you. So we were talking about these straight chain, what is that doing there? Straight chain forms. And it turns out that that's not the only form that these simple sugars take in solution. In fact, there's an equilibrium between or among the straight chain form and a few other structures as well. I'm not all that concerned that you memorize them, but I would like you to be aware of them at least. Here we go. So even let's expand that so that people can see it better. And these would be they. So I want to make it fit all on the screen. So here's your D glucose. We just drew that. There are two other types of structures that they can take on, cyclic forms. One of those cyclic forms is a six-membered ring, and we call those things pyranoses because they resemble the structure of pyran, which is a six-membered cyclic compound. And the other are the five-membered forms, which we call furanoses, because they resemble the structure of furan. Furan is this five-membered cyclic compound. And so what I've given you here is sort of a step-by-step way that you can go from, that shows how you go from the straight chain form and close that six-membered ring. The reaction behind it is one we just talked about in chapter 9 on aldehydes and ketones. What's going to happen is one of these OH groups is going to form a hemiacetal with the aldehyde. And we just talked about that the other day in class, how that can happen. So that whole process is exactly the same as with as if it were any other OH group. I will be honest, and the reason that I'm putting this in the class notes is it's my experience that unless I can prove how it is that you get from here to here and that you really, this really is valid, and I didn't just make it up, unless I can prove it, there's a large percentage of students who just won't believe it and will not be willing to follow me. So that's why I've put this in here. And something which I'm not proud of is honestly, that whole question of exactly how does it bend and so forth, it's something that's never particularly interested me very much. Maybe because I just sort of think, oh yeah, there's a way to bend it and you get there and you're fine. And it's something that I never really looked into very much, except insofar as putting these structures out there. So I would say if that's you, if you need to be convinced that you can get from here to here and thus to the pyranoses, then there you go. I've shown how that works. This, by the way, is another, yet another type of projection that you can use to draw sugars in their cyclic forms. And we actually used this already with ribose and deoxyribose in chapter 18 on the nucleic acids. And these things are known as Hayworth projections, H-A-W-O-R-T-H, Hayworth projections. And like I said, I'm not really concerned if you can draw these. I would like you to be aware that these cyclic forms exist. And this is one of two perfectly valid ways to draw these cyclic forms. These Hayworth projections are very nice. Sometimes they even make these lines absolutely straight, you know, kind of, oh, if you will, almost a tangent to the six-membered ring. So you'll see them drawn that way too. The thing that's very nice about Hayworth projections is that it's very clear what's pointing up and what's pointing down. And that turns out to matter, especially with the OH group in carbon 1. Carbon 1 used to be the aldehyde, but is now a hemiacetal. But that OH group can point either up or down. And so it's very easy to see that on the Hayworth projection. It's very clear when things are up or down. And you'll see these mentioned too, the alpha and beta anomer. Anomer is just a special kind of isomer that we find with sugars. And it turns out that the alpha anomer has the OH pointing down, the beta anomer has it pointing up. And I have a stupid mnemonic device for that too. It may be too stupid to do you any good, but maybe it will help some of you. The way I always remember which is up and which is down is, so to speak, the vowels and consonants do not go together. So the alpha anomer, alpha is like a vowel, it's like an A, and so you would think it would mean it's pointing up, but no, it means the OH is pointing down. And likewise, beta is a consonant, and so, but rather than the OH pointing down, because D is a consonant, it's pointing up. So the vowels and consonants don't go together in terms of which is up and which is down for alpha and beta. And this kind of thing is referenced a lot in biochem and in biology classes. So I feel it's kind of my job here in this organic chemistry class to go into these structural ideas that they will never go into in biology classes. And I'm not saying they're wrong or they're bad people. They just have a different focus. But I feel it's my job at least to explain this sort of thing to you. And we'll get into another way to draw this type of compound in just a moment. I won't have too much to say about the furanoses, though I did point out how it is that we get from the straight chain form to the furanose. In this case, it's a different OH group that we form the hemiacetal with. There's alpha and beta forms of that as well. I sure don't care if, I mean, I don't think I care very much if you memorize these, but I care even less if you memorize these. But I just wanted to point out what those structures are and to show you where they come from. And in truth, if you were to dissolve, say, glucose in water, D glucose in water, what you will get is an equilibrium mixture of all of these things. There will be both the alpha and beta anomers of the furanose, both alpha and beta anomers of the pyranose, and maybe a couple percent of the straight chain form. And there will be a rapid equilibrium. Everything will be switching back and forth between all those forms. And the exact amounts are known. You know, you could look up what the amounts are in 1 molar glucose at room temperature if you wanted. I sure don't care if you memorize that, but if we wanted to know it, we could all of us look that up. Good. One last thing. It's also certainly possible to draw these pyranose forms, and we'll end with this, using chair forms like we did with cyclohexane. And so that's why I think learning about cyclohexane being in the chair conformation is useful, because we can do the very same thing with these sugars. And as long as we use this form of the chair, all I've done is replaced a CH2 with an oxygen. And so these are both D glucose in the beta and alpha anomeric forms respectively. One last thing I'll end with, which is I'm entirely certain a coincidence, but it certainly is a very happy coincidence, which is look at where the OH groups are, and also the CH2OH group, which is carbon 6. You will notice that all of these other OHs, except for the anomeric one, that can vary. That can be either up or down, and therefore either axial or equatorial. One of the things you'll notice is the other 4 groups on D glucose are all equatorial. So I'm not going to make you memorize this, but memorizing that one is actually pretty easy as a result, because it just so happens that for D glucose, all of those non-hydrogen groups, again, leaving out the anomeric OH, that's different, but all of the other ones just so happen to be equatorial. I'm sure it's just a coincidence, but it certainly is a happy coincidence. And I think that's about it. So yeah, I'm really only concerned for us with the straight chain form. And I think that's about it. That gets us into a good position to start getting into the reactions of simple sugars next time. But other than that, I'm out of time. And yes, I will certainly get all your class grades updated by the end of the week. Friday or Saturday, absolute latest. So other than that, see you all on Friday.